In this tutorial session, we're going to look at a two-dimensional diffuse limited aggregation algorithm. And the code that I'm going to test today is actually pretty short, but it has a lot of different qualities and dynamic interaction with the user. So I'm going to first present you a demo and show you what's happening with the code. And we can freeze the simulation at any time we want, you can see. And it's basically spawning some particles that are moving in the vertical direction on the screen. And when these particles meet any adjacent particles that are frozen, they freeze themselves as well, so that we get kind of initially I'm going to show you how we can test this in kind of a two-dimensional growth direction, but then we're going to do it in this type of raining model, which is going to accumulate in the vertical direction. So I'm going to start a new sketch, and we're going to do this from scratch. So basically, we're going to need two main functions first, which are going to be setup and draw. So I'm going to type in void setup for the settings of my sketch and void draw for the simulation. And to keep track of what's happening with the grid, I'm actually going to define a float array, double array. So I'm calling this as a Cellular Automata because we are going to work with a grid. And if you haven't seen other tutorials where I also discuss some Cellular Automata principles, basically I'm going to simulate the particle simulation as if it's a two-dimensional discretized Cellular Automata grid. And the reason why I'm starting a float value, a double array, is because I want to keep kind of a coefficient value for each index of the grid, right, on the screen basically. And I'm going to be storing eventually two values that determine either a cell is frozen, or it's alive, or it's in motion. So that's going to be the type of aspects of the simulation. And I'm going to define a resolution for my cells and an AS parameter, which is going to be the array size. And we can basically determine that through the resolution. So I can actually specify some sort of a parameter here. Let's call it resolution is 600. And I'm going to start a sketch at 600 by 600. And then a array size is going to be 600 divided by res divided by dimension. So it's not as convenient as I would like it to be because we cannot directly input a parameter here. It gives kind of an error for the new processing sketch, but this would do the trick. And then I want to initialize my Cellular Automata grid as a new float array. And this is the way to start it in a two-dimensional. And I want to initially start it with a frozen cell in the middle. So I'm going to type it array size divided by 2 and array size divided by 2. So this is the index for the cell in the middle of the screen, and I'm going to store the value 1 there. So basically, we're going to either store 1s or 0s in the Cellular Automata grid, and when it's active and moving, it's going to be 0.5. And I'm going to get to that in a second. So this is going to be a frozen cell. Now let's see what happens when I run this sketch. So initially you can see that we're not drawing anything, so we just get a 600 by 600 grid. Then in the draw, we can start drawing the sketch. So I can do background. Background is going to be 255. I have a little typo, so let's fix that. And then what I want to do is go through the list so I can traverse my array. So if int I equals 0, for int I equals 0, I smaller than array size I++, and I want to do the same for j. You can basically define any parameters here you want, but I tend to go with the convention. And I want to check here if the cell at the ij index, and we can actually store this first. So for instance, I can do float value equals the value of the cell, and I want to check if this value is something so that we can draw there. So if this value is 1, if this value is similar to 1, then it's basically a cell that has frozen. So what I want to do is draw a box there. So I'm going to do fill 0 and stroke 0. So I want to draw a solid box. And after the for loop, we can, after the if statement, we can go here and draw a rectangle there. So the rectangle is going to be I times dimension, j times dimension. And because I'm also adding a stroke, I'm going to do dimension -1, dimension -1 for the width of the rectangle. So let's see what's happening now. So when I run the sketch, we initially get the background as 255, but basically I didn't do anything for the other cell states, right? So everything is, I think, at 1 now, although I just set the one in the middle. So we can also do if another statement and call it else, else if val equals 0, 0, because I'm checking for the floating values. Then what I want to do, I think the problem is we are not doing any type of change after the fill is set. So that's why it's kind of coming back and applying the same type of fill. So we can actually do here no fill, because we don't want to draw anything there, and no stroke. So I should be just seeing a simple a white canvas with a black dot in the middle. So this is the cell in the middle that we set to be 1, right? So that's the frozen cell. And if I change the dimension for the grid size, then you see it's a larger cell, and it's located in the middle. Now what I want to do is kind of create a function where we can animate the screen. So for instance, we can add another type of check here. Let's say else if val equals 0.5. You can also do else. Basically any value other than these would suffice, right? So I can just say here, and I want this to be gray, so that we know we are basically trying to differentiate cell states between 3 conditions, right? So either they're frozen, they're black, they're white, means it's empty, there is no cell there, but we are still visualizing that space, and as gray, which means the cell is active and it's in motion. And for those, I'm going to add a fill at 125, which is going to be a light tone of gray, and I'm going to add 125 as well. So this is, we don't have anything at 0.5 yet. We can actually define something here. For instance, we can do the left top, or let's say 5.5 to be 0.5. And you can see that cell has a different value, so it gets gray color. Now the first thing I want to do is manually input these cells. So let's go down and do void mouse pressed. And for these, every time I press the screen, I want to change the state of a cell at that location. So I want to first find that location. So we could do mouse x divided by dimension, and then I can do mouse y divided by dimension, and I want that to be 0.5. So every time I click somewhere on the screen, I want there to be a gray box, right? So that's what's happening. And initially I want the DLA to work like this. So I want to input cells that are going to move in the X or Y direction. So they're going to be in motion. So they're going to look like flying bees actually. And then they're going to stick to any type of frozen cell, right? So we need a way to check if a cell is adjacent to a frozen cell or not. So before doing that, I need to have a method where we can move these cells. So let's define a movebox function for int I and int j. And inside of this, what I want to do is find the basically change the state of the cell. So I can simply do ca I j. So I want to override the state of this cell to be 0. And then I want to move it in a random direction, right? So to find that random direction, we can just type up kind of a relocation in the x direction. So I want to add to its current index some amount. Let's say it's going to be between -2 and 2 in the x direction. And I'm going to copy this as well and add some random value to its j as well. So basically I want each cell to move in 2 directions, so x or y directions, and I'm throwing some sort of random value here. So basically I want to get a random vector direction in x and y, and then I want to relocate the cell in that state, in that location. So let's find the actual location. So basically I don't want these cells to go outside of the boundary, especially when I'm rewriting them into my array. So I want to first check if they are within the boundary, and to verify that we can just check if they're within the limits. So x needs to be greater than 0 and it needs to be less than this index, so that we can make sure that it's within our Cellular Automata list. And I need a copy of this one for my y as well. Then what I want to do is basically we can alter the state, but this is already we can already state something here. So we can say, for instance, 0.5. So I'm basically going to override the new location of the cell as 0.5, right? So initially I got this location as I and j, and I made it 0, meaning it's going to be empty. And I found the new location for the cell and made it 0.5. So this is always going to be within the grid. So we need to input this somehow in the draw function. And one way of doing that is we only want to move the boxes that are gray, right? So what if we can add it here, else, and we can say move box I and j. So as simple as that. And when I run it now, every time I put a cell, it will basically start moving in the x and y direction, right? So we are basically getting 2-dimensional rotation now. It actually destroyed that cell because it moved through it. But we're going to make it in such a way that when it hits a frozen cell, it's going to freeze. And one way of doing that is by checking within the movebox command. So we need to check for adjacency. So imagine here, if I check neighbors at x and y, right? So if this function returns true, if one of your neighbors are alive, then you can simply freeze that cell state, right? So we can do something like this, equals 1, so that will become frozen. If they're not alive, then you can keep moving, so you can stay 0.5, so you're basically still moving. And I basically need a way of checking these neighbors now. And that function will return a Boolean because it's going to return a true or false. So I want to check for neighbors at int x and int y. You can always change these inputs within the function, so I can call them with whatever I want. I can rename them here a and b as well and use those parameters inside the function. And inside of this, I want to use something similar to the Moore neighborhood, right? So I want to check in both directions. So I want to check the left direction, right direction, top and bottom, but I have 8 neighbors for each cell. So I want to be able to check for all of those. And one way to check for them is you start by defining the lowest value for your I, which is going to be I minus 1. And then I want to go to the maximum value it can achieve, which is going to be x plus 1 or array size minus 1, right? So the array size minus 1 basically maintains that we stay within the Cellular Automata grid. And then I simply increment it by plus 1. And I can make another copy of this, but this time this is going to be for j, and this is going to be y, and this is going to be y plus 1 and j plus plus, right? So this makes sure that I'm actually checking for all of my neighbors in the 8 neighbors for a cell. So I'll check for the left, and I'll check for the right, I'll check for the bottom, and I'll check for the top as well. So that's how it's going to work. And we want to check if the cell at that location, which is going to be I or j, equals to 1, then it means there's an alive neighbor. We can simply return true. And after this, if we haven't found any, we can simply return false. So that means we don't have any alive neighbors. And when this happens, so every time I'm moving a box, I'm going to check for my neighbors. And if I have an alive cell, then I'm going to, if I have a frozen cell, then I'm going to freeze the cell, basically freeze the cell, or keep moving, right? 0.5 means it's in motion, 0 means there's nothing there, so it's just empty space. And that's why we need a frozen cell in the simulation, so that we can make sure I'm getting an error. So it says out of bounds. Let's see, this is actually correct. Let's see here. This seems to be working for me, but let's see where we have messed it up. Oh, this is checking for I. I forgot to make this j. All right, so that fixes it. And let's add some more. So when they get closer, boom, it becomes frozen, right? So here they're flying in random directions. And I can add a lot more. And you will start getting a DLA behavior. Basically, this is going to keep growing in a way that the tentacles that are outward, they're going to collect more particles. So we can also start automating this. We can say, for instance, rather than clicking anywhere, we can make this randomized, and we can make it embedded into the simulation. So I can say if frame count mod 2 equals 0, so for every 2 frame counts, we can simply get a random location divided by dimension. So let's see if this would work. It might actually need to be converted to an integer. I think we need to convert this to an integer because random gives us a float and we're dividing it by dim. So I need this to be like that. So now we're going to spawn particles automatically, and it's going to grow a lot faster now. Right, so you can see wherever you spawn, it immediately attaches to something. And to get like a better simulation, we can simply reduce the dimension. So these particles are attaching wherever there's a dead particle. So this is in essence kind of a DLA. Normally DLAs work with some sort of radius of influence, and the more the simulation runs, they actually enlarge. And one way of changing the input would be, rather than using, let's say, kind of a frozen cell in the middle of the screen, I can actually make all the cells at the bottom of the screen to be frozen. Right, so for that, I'm going to disable these two lines, and we can simply call a reset function here. And I can type up void reset, and inside of the reset, I just need a simple single for loop, I smaller than array size and I++. And inside of this, I'm going to turn, let's copy this guy. I'm going to turn the CA at I, but a array size -1, right? So this is going to be 1. So these are the indices for the bottom row. So if I run the function now, you see I have the bottom row to be black. And every time a cell is moving towards the bottom, now it's attaching. And we can actually bias the movement a bit more as well. So if you go down, rather than giving this sort of movement for Y, because you know 0, 0 is left top and 600 by 600 is bottom right for the pixel dimensions, we can actually always move these cells in the positive direction. So if I make this 0, and then if I run the simulation, they will always fall down, right? So this will accumulate the cell, the DLA algorithm a lot faster. And one last thing I added was kind of an animation. So we could do void key pressed. So every time I press any key on the keyboard, we can basically turn on or off kind of an animate function. So we could do boolean animate equals true. You can start with a true condition, and inside the before the move box, we can check for if we are in the animation mode, so that we can move our boxes or not. Right? Otherwise, we're just going to keep visualizing things without moving them. So every time I press a key, we're going to keep spawning. We could also do, like here, we could type and animate, right? I also want to check for if we are animating or not. So we can simply freeze the simulation anytime we want. So there you have it. This is two-dimensional diffuse limited aggregation implemented on a vertical simulation. And you can always play around with these parameters. It's a bit tricky with this algorithm to change these movement parameters. I mean, I can make them to move 1 pixel at a time, but sometimes this gives kind of a stationary value for most of them, so that's why I kept it at 2, and sometimes it also goes past certain cells, which can cause some sort of mistakes. But I think overall it gives you kind of a nice distribution for the cell behavior and accumulation of data. So I hope you enjoyed it, and thanks for watching.